Our next topic is BPSK modulation. BPSK modulation. Well, why? Before going to the actual topic, let me give you an example, because the modulator, the signal which is at the modulator has to be represented by some waveform, and then at the receiver, the demodulator, an important process is the detection process for recognition of these signals which are transmitted by the transmitter. So if you observe your transmitter, if you have a transmitter and it transmits signal to the receiver. Usually at the transmitter, the data would be in the form of some 1-0 sequence of ones and zeros. Because if you see your data, usually it is in the form of ones and zeros. It's a sequence of ones and zeros, whether you save it on your hard disk or you have it on your mobile phones, your voice data. Ultimately it is converted to the 1-0 form. Whenever the data is saved, it is a sequence of ones and zeros. So the target is to successfully for a digital communication for communication system, the target is to successfully transmit this data to the receiver, so that receiver can recognize that the data which comes from the transmitter is actually this sequence, the given sequence. Well, how this process takes place, let me give you a very simple example. Suppose you have a baby, and you are trying to teach him the shapes. So you can show him the shape of a car, and you can say, okay, this is the shape of a car, and the baby recognizes the shape. Similarly, you can say, you can just show him the shape of a bus or a toy of a bus, and you can say, okay, this is a bus. Right now, to test him whether he understood these shapes, what you can do, you can just take some other shapes and ask him whether he recognizes those shapes or not. For example, if you give him a shape of an accidental car which looks like, suppose an accidental car which looks like this. Suppose this is an accidental car, right? And it looks like this, and you ask him that whether it is a car or a bus. So by comparing this car, what the baby would do, it would compare it to both of these shapes which is in his mind now, and it would tell you that, okay, his decision would be a car because it looks like a car, right? But if the car is badly reshaped, and instead of this the car get this kind of shape, suppose it is, this part is completely destroyed, suppose this part is destroyed, and the car get this shape, so something like this, right? And now you ask him, okay, whether this is a car or a bus. So if you see, this part is already, I told you that this is the rear part is accidental and it is destroyed. So now it looks, if the baby compare it with the car or a bus, he most probably he would declare it a bus rather than a car, right? Why? Because now the shape looks like this, and this, after comparing the accidental shape, because it looks more like the bus, so the baby may declare that it is a bus. Similar process is going on the modulator and demodulator. We have to transmit ones and zeros. We select a waveform for 1 and a waveform for 0 and transmit it over the channel. Well, now at the receiving end, what happens? The receiver tries to detect a 1 and a 0 based on the distorted waveform, based on the noisy waveform, and if it actually performs this correlation, the process of correlation, matching. The receiver matched the signal with the existing replicas. This is just like existing replicas of the signal, and after the comparison it declares whether it is a 1 or a 0, a waveform of a 1 or a waveform of a 0, and it may be correct if the waveform is not destroyed, just similar to this car. If it is like this part is accidental but it is still there, and it may declare it wrong if the waveform is too much destroyed, such as this car. So this is conceptually the modulator and demodulator would work this way. Now if I go to the actual topic of BPSK modulation, we actually have a sequence of ones and zeros at the transmitting end, and we choose waveforms for representation of a 1, for representation of a 0 and representation of a 1, and the waveform we choose is S1 of t and S2 of t. These two waveforms are selected for representing a 1, which is a cos of omega ct plus theta 1, and here it is a cos of omega ct plus theta 2. And if you see these two waveforms, they differ only by this theta, right? The waveform differ by this theta. So in BPSK we have a sinusoid for S1 of t and S2 of t, and they differ by theta, and this difference is theta 1. Usually you will see that we will take theta 1 equal to 0 and theta 2 equal to pi degrees. So our waveform, these two waveforms will be used, theta 1 with 0 degree and theta 2 pi degrees. Now you can represent your S1 of t, you can represent S1 of t, you can rewrite it like this, cos of omega ct, and you can rewrite S2 of t as a cos of omega ct plus pi, and if you observe this one, this is just minus a cos of omega ct. So these two, cos of theta plus pi is minus cos of theta. So this mathematical identity is used, and you can see that we have the two signals S1 of t and S2 of t, and they differ by the phase. That is why another important property is why we call it the binary phase shift key. If you add a phase of pi to S1 of t, if you change the phase of S1 of t by pi degrees, it would become S2 of t. Similarly, if you change the phase of S2 of t by pi radians, if you change the, not degrees, radians, right? So if you change the phase of S2 of t by pi radians, it would become S1 of t. So you can that's why we call it the binary phase shift keying. And well, we can rewrite the same signals as we can rewrite the same signals as S1 of t. We can represent it as S11 psi1 of t. Now we will use the same psi1 which I mentioned earlier, that sinusoid, right? And S2 of t, can be written as minus S21 psi1 of t. Now very important, if you see, this is just one-dimensional signaling, right? The binary phase shift keying is one-dimensional signaling. You just need psi1 to represent these two signal points, S11. These are the scaling factors you can represent here. These are the scaling factors for psi1. So as I mentioned earlier, that our psi1, what is psi1? Psi1 of t, as in my previous lecture I mentioned that this is psi1 of t is 2 over t cos of omega ct, right? Cos of omega ct. So this is our psi1 of t, and you can represent your signal in this form. You can find out the value of S11 and S21 for BPSK. Well, these are also known as antipodal signaling scheme. This scheme is known as antipodal signaling scheme because you just need psi1 of t to represent these signals, and if you draw it on the axis psi2, we do not need psi2, because if you see over here, you can just represent a point here which is positive S11, this one, and a point S11 times psi1 of t. Similarly, you have a negative, you have a point here for psi1. The image is represented by S11 and S21. So you have the point S1 would be here, and the point S2 would be here on the psi1 axis. So clearly these 2 points are opposite, they have opposite polarity. That is why it is known as antipodal signaling scheme. And what actually we would verify that this length, this is actually equal to the square root of e. Similarly, this one, this is equal to square root of e. So if you have these points, it means the coordinate of this point can be written as square root of e0. No vertical component, right? Similarly, here it would be, if I try to write the coordinates, it would be minus square root of e and 0. You can find the energies of these signal points. Just try to find out the energy of S1 and the energy of S2. So if you are interested in finding the energy of your BPSK signals, we call it BPS. These S1 and S2 are called symbols, right? So you would see the books and the literature use the word symbols for these signal points in the Euclidean space. You can find the signal of these each symbol. So if you are interested in the to find out the energy of this symbol, you can just find it out. Now we, instead of writing minus infinity, I would say 0 to t, because this is the time period where our signal exists. So we find the energy of the signal by squaring it and integrating it over the in the given time period. So if I square it, it would be a square cos square omega ct dt. So if you try to solve this integral, this a square 0 to t 1 plus cos 2 omega ct over 2 degree, and if you solve it you will get a square t over 2. So this is the energy of signal S1. Similarly, you can prove that the energy of S2 is also a square t over 2. So if we the energy is e square the energy is a square t over is the energy for a BPSK symbol, whether it is S1 or S2. So you can find out this energy if you see the points now, the signal, the coordinates. If you are interested in finding the coordinates, because you already have the expression for energy, right? The same expression, the same energy can be found from the expression where we are using basis functions. So our signal points would be square root of this e, right? So square root of e, these are the points for S1, and this would be a t over 2, right? This is the signal point. This is 2. This is our signal point. This is for S1, and similarly for S2. For S2 it is minus of negative e, so this becomes negative e. These are the points on the x-axis. So these signals can be observed, the antipodal signals can be observed on psi1 axis in the Euclidean space. So next we go to the BPSK modulator. So I would show you the BPSK modulator in the next lecture.